All right. So now that we understand sort of how computers work and we understand generally how you might teach a computer how to do sound, what we're going to talk about today is how that actually works. So what are the pieces involved and the processes involved in actually doing sound on a computer now that we understand how you could encode it. And then I'll talk to you about this project I emailed you guys out. So this is just a very simple diagram of now, what a digital audio workstation might look like. So you have, you've got your computer here in the middle, and usually you want to have an external hard drive. We'll talk about that in a minute. And the important bit is this thing called the audio interface. In this case, we're calling it an audio MIDI interface because it's doing both. But this is going to be some sort of box that plugs into your computer that does those analog to digital conversions and digital to analog conversions, which is the important stuff. So in this case, like we have, these Thunderbolt Zoom interfaces on these workstations that do that. You've got a Mo2 FireWire interface over here. This is a box. It's a box that usually has some XLR or quarter-inch or other audio connections that let you put sound into a computer and get it out. Okay. Sometimes they'll also have MIDI inputs and outputs on them, which you can use to hook up MIDI devices. Although you can have dedicated MIDI interfaces, like I've got this one here. This is just a USB MIDI interface. Gives you 2 MIDI inputs and 2 MIDI outputs on a USB cable. Okay, very useful. So all the other stuff sort of plugs into that. So your microphone plugs into some sort of input, sound input on your audio interface. Your monitor loudspeakers would plug into some sort of audio output on that. If it had a MIDI input, you could hook up a MIDI keyboard to that. Your headphones, there'd be a headphone output on there. So this interface, we call it, is really the thing that lets you get the sound in and out of the computer. And the way in which that connects to the computer is going to be different. You can get ones that do it over a USB connection. You can get ones that do it over FireWire. Those little Zoom ones do it over Thunderbolt now. You can even get ones that involve, PC card slots. If you've got like a tower computer, you put a card slot in. That's great. It's not entirely convenient if you've got a laptop, but if you've got a nice big computer, that should be really helpful. But it's going to be some way of you connecting that thing to your computer. So if you're going to buy one of these, you need to make sure that whatever its interface is something that you have on the other end of your computer. So if you go buy, for example, a Thunderbolt interface and you don't have a Thunderbolt port on your computer, you're going to have a tough time interfacing that box with your computer. Okay, so that's one of the most important things to keep in mind when you're doing this, thinking about this is, okay, can I actually plug this into my machine? And does it come with the cable, or do I have to buy the cable separately? Whatever. There are lots of opinions out there about what is the best way to interface audio with a computer. We used to think it was FireWire, although we're finding that over time FireWire has proven not to be all that great for audio interfaces. It's pretty great for hard drives, but not so great for audio. And some of that has to do with the connection itself, like the actual physical connectors are not designed real well. They're not very secure, and that's proven to be problematic for audio. So we tend to sort of like USB these days for small interfaces. FireWire for larger ones that have, if you want more inputs and outputs, FireWire is going to be a bit more reliable there. And now there's a lot of these new Thunderbolt interfaces that are coming out that are looking pretty promising too. Although I think at some point that's all probably going to be supplanted by AVB. So as you may or may not know, AVB is this standard that is being developed where you could use standard networks, computer networking, to shoot the audio around. So essentially you're going to use the Ethernet connection on your computer now for your audio interfacing. You can get little pieces of software that will let your sound programs send audio through your Ethernet connection. In fact, most new Macs come out of the box with this capability, so you can turn on AVB for your network port, and it'll shoot audio down there. Now you gotta have something on the other end to receive it, but you can get it. The most common, the ones that most people are using these days that do that just as a gee whiz kind of thing, Focusrite is making some interfaces. We have a couple of them called RedNet interfaces. See if I can get it to pull up here. And I believe Motu just came out with an AVB one as well. Should pull that up and see.
What does AVB stand for?
Audio Video Bridging. Yeah, so here's their new AVB audio interface. So it's got Thunderbolt and AVB. You can use whichever one you want. Let's see if we can find a picture of the back of it. Yeah, here we go. Come on. Oh, and USB. It's like it does everything. Ah. Can you just show me some pictures of it? One of the things I don't like about Motu is they're just like, they often miss the point. Okay, there you can kind of see it. So you're actually plugging a Cat5 cable into this interface. It's just like a Ethernet connection. And it also has USB there, and some of these might have Thunderbolt as well. That's one example. The nice thing about this is that you could actually have these devices talking to multiple things, right? So you could have multiple interfaces all around your room or whatever that are just pulling different streams off of this AVB network. So that's kind of interesting. It's still being developed. There we go, Ethernet audio interfaces. RedNet, there we go. Oh look, they've just come out with some new ones. But these are interfaces that these use what is called Dante, which Dante is kind of a precursor to AVB. Eventually Dante will become AVB. So you can see you've got an Ethernet port here, and then just some DB25 connectors that you could get 8 inputs and outputs there with a snake tail that you could plug into that. So it's pretty cool now. And a lot of hardware now is getting that. So like you can get cards for mixing consoles and processors and things that have AVB ports on them, or Dante ports on them. Like we have wireless microphone receivers now that have AVB ports on the back of them. So eventually it's going to get to where all of your, this AVB thing is going to become the digital version of the XLR. Okay. And everything's going to talk this language. It's not, most of your digital snake protocols now are all proprietary, and AVB is ultimately going to be an open standard. So assuming you've got the switch that can connect them all together, you should be able to have all your devices talking to each other in digital using Cat5 cable. So that's kind of a relatively new development, and that's not in this case, if this was an AVB interface, this connection here would be an Ethernet connection. Okay, but it could just as easily be a Thunderbolt or a USB or a FireWire, or even something else. I mean, there's other things out there that are less popular but proprietary in nature. All right, so let's take a look at what happens here. So here's just another example. I've taken the MIDI keyboard out of it for now, because that works a little bit differently. We'll talk about MIDI in a few weeks. But here's all the different, because there's inside of each of those boxes in that larger diagram, there's lots of things going on. Okay, so we're just gonna go through each of these and talk through it. So this first thing is the microphone, and hopefully we sort of know what a microphone does at this point. But it is a transducer. It takes that acoustic energy and converts it into electrical energy. So it takes a sound wave that's happening in the air and creates a voltage wave out of that. And so that voltage then is fed into your audio interface, okay, which is the big black box here. And the first thing it's going to encounter is this thing called a preamplifier. And this is, again, not a new thing. Preamplifiers have been around as long as microphones have been around. But the preamplifier, the idea there is you're trying to increase that voltage level. You want to get that voltage as hot as you can get it before you ask the computer to digitize it. Because remember, the computer is going to try to assign numerical values to those voltage levels. And you want to get as high resolution as you can that way. The best way to do that is to get that voltage as hot as you can get it. Although, as we discussed, there are some strategies, reasons why you may want to be conservative in that setting, as we talked about last week, that sometimes you don't necessarily know how loud things are going to be. And if you're recording at high enough bit depths, you can get away with cheating a little bit on this. But generally speaking, you want to crank this up as hot as you can without clipping it. That's the goal. And so, depending on what interface you have, there's going to be a knob on the front of it. Oops. So we got some pictures of a couple interfaces here. There's going to be some sort of knob on this that'll let you turn this up. Although, interesting thing about AVB now is it has built into it a control protocol that you could use to potentially remote control digitally remote control preamplifiers, which would be kind of cool. Assuming someone makes one. But that'd be slick. All right, so that's first. That's the first thing that happens inside that interface is you're gonna crank that voltage with a preamp. Okay. Now, once it comes through the preamp, the next place it's going to encounter is your ADC, which is your analog to digital converter. And this is the thing that does what we talked about last week. It's a little chip, and it senses voltage and assigns a number to it. Okay? And these are cheap now. I mean, it used to be that converters were really hard to come by and were very expensive, and now they're very inexpensive. You can get really high-quality converters for very, very cheap. There are, you can certainly, if you are interested in spending a lot of money on converters, you certainly can still. There are places that make really very expensive ones, but by and large, the converters are not the problem anymore. The quality's gotten pretty consistent there. Okay, so there's one thing to know about analog to digital converters is there's a slight bit of latency involved in this process. Okay, so it takes a little bit of time for the computer to do this, for the converter to do this, and people who design these circuits, that's one of their quests is to try to get that latency down as much as they can. The rule of thumb I usually go by is that, although some of them are getting better now, is it's about a millisecond per conversion. So every time you do an analog to digital or digital to analog conversion, you're gonna lose a millisecond. Okay, and usually that's if we're doing live sound in a theater, that's not a big deal. I mean, we usually are adding extra delay to our systems anyway, so latency isn't going to kill us. But when you're in like a environment where you might be recording, for example, latency can be problematic once it builds up, because if you've got, if you're tracking things and you're recording things one at a time, and you've got a musician listening back to what's been recorded and trying to play on top of that, if there's enough latency between when they do whatever they're doing and then when they hear it back on top of the track, that can be really tough for them to play on tempo and everything. And so you got to be careful about that latency. And there's lots of places you can pick up latency in the signal chain, as we'll see. But generally speaking, you're going to pick up a millisecond just in the digital or the analog to digital conversion. Although I'm seeing that start to go down now. You're seeing converters, inexpensive ones even, get down to almost half a millisecond these days. Not quite half, but they're getting better. Okay, so once it goes through there, now it's digital, and you can see, we're indicating that here with, it used to be this red analog wave, and then coming out of there is a blue stream of zeros and ones, okay, which is what the computer likes to see. It counts in binary, as we'll learn in a couple of weeks. Okay, so that stream of zeros and ones that represents the voltage values for each sample that it took goes into this controller chip, otherwise known as the digital signal processor. And this is another chip inside of the device. And what the controller is going to do is it's sort of like the CPU for your audio interface. Okay, so its job is to take that data coming in off of the converter and figure out what to do with it. Okay, so it's responsible for routing it through whatever interface you're using to the computer, whether it's Thunderbolt or FireWire or whatever. It figures out how to format that data in a way that can shoot down that wire and be interpreted by the computer on the other end. So there's going to be a certain amount of traffic steering that's going to happen here. And that's what the controller, and there might be some processing involved in there too. There's some interfaces that you could be applying EQ or reverb inside of the interface before it ever goes into the computer, for example. That's all possible. It's not recommended because once you do that in the interface, then you can't undo it later in the computer. But it is possible to do that. Okay, so once it, ultimately the controller chip is going to figure out how to get that data to travel down this data cable, which is the green stream, into the computer. And the computer's going to have this driver. Okay, this is going to be a piece of software that's been written that teaches the computer how to talk to your interface. Okay, so it's a piece of software that says, hey, there's this interface out there. You're going to see it showing up on the USB bus or the FireWire bus or whatever, and it's going to be shooting you data in this format. Okay, so this is what the streams of zeros and ones coming off of that are going to mean. And here's how you would assemble that into audio. Okay, so that's what the driver is. There's lots of different ways to go about this, but in most cases what happens is rather than requiring each manufacturer of an interface to figure out exactly how to get their interface to talk directly to the computer, the manufacturer of the operating system, whether this is Microsoft with Windows or Apple with Mac OS 10 or even Linux to a certain extent, who's ever running that operating system will create an audio engine for that operating system. And all the manufacturer of the interface has to do is create a driver that operates on that engine. So, for example, with the Mac, it's Core Audio. Okay, so if you're going to make a driver for an interface, you just have to teach that interface how to speak the language of Core Audio. And if you can do that, then Apple takes over what is involved in getting all that to talk to the CPU, the computer, and the RAM, and the hard drive, and all that kind of stuff. So all you have to worry about is how to get it to talk Core Audio. If you're on the Windows side of things, you're either going to do what's called ASIO, which is another sort of, that's a third-party kind of thing. Steinberg, I think, was the ones that came up with that initially. That's used for lower latency, multi-channel audio. So most professionals use that. But there's the one that Microsoft did is called DirectX. And so you could choose to write a DirectX driver for your interface or an ASIO driver for your interface. Most of them do both. And so what that means for you, the end user, is you ultimately have to get that driver, right? You have to download that Core Audio driver or that DirectX driver or that ASIO driver for your interface so that it can talk to that system, and then the operating system takes over figuring out how to get the computer to talk to it. Okay? So assuming that that's all been negotiated, you got the driver installed, and now the computer knows how to talk to your interface, and everything's hunky-dory, the data's coming in, and it's making sense out of it, and there's no major problems. What's going to happen is your audio now that's coming in off your microphone is going to it's going to go straight to RAM, okay? So it's going to come in off of your USB or whatever, and the driver is going to direct it to RAM. And there's going to be created in RAM what's called a buffer. And the reason you need a buffer is because, remember, that CPU and that computer is doing all kinds of stuff. It's not just doing your sound. It's got a lot of things lined up that it's thinking about right now. It's trying to run a whole operating system. It's trying to find out what time it is. It's pinging Twitter to figure out, what's going on there. I mean, whatever else you've asked your computer to do all the time in the background, which there's all kinds of things you may not even realize you've been asking your computer to do in the background. But it's doing all those things. And you never know when a little email push is going to somehow redirect the CPU's attention temporarily away from your audio stream. So you don't want the audio to just drop out because the CPU can't pay attention to it for a second, or a microsecond, as it might be. So what happens is we build this input buffer. So all that data kind of collects up in there and creates this reservoir, so that as the CPU's ability to process it kind of waxes and wanes, ultimately it's what's delivered to you is steady. So the CPU can speed up or slow down, and ultimately what comes out of it on this other end is a steady stream. It isn't interrupted, and that's because we have this buffer. Now, to some extent, you can control the size of this buffer in most software that you're using. So certainly in Logic, you can go into the audio driver settings and you can say, how big do you want your input buffer to be? The bigger the buffer, the more reliable your system's going to be, right? The less likely you're going to end up with a dropout. However, the bigger the buffer, the more latency. Okay, because remember, if you're lining up the audio in that RAM buffer, that's all for however long that is. That's the amount of time you have to wait before you get to hear it. Okay, so if it's a 1024 sample buffer, you've got to wait the amount of time for 100 or 1024 samples to tick before you'll hear the first one. Okay, so you've got to find a balance between, what amount of latency am I willing to live with, and compared to what amount of potential volatility am I willing to tolerate in my system. What's that balance between reliability and latency? And that's where you get the buffer. Generally speaking, you want very low buffers for recording and very high buffers for playback. Because when you're listening back, the latency, it doesn't matter, right? The fact that you hit play and, a fraction of a millisecond later, you hear it, that's not a big deal. But when you're recording, that can be a big deal. So you want as low latency as possible when recording. So usually, what I'll do is I'll knock that input buffer down quite a bit when I'm doing a recording, unless I'm trying to record, 20 things at a time. At that point, I may not be able to get away with that small of a buffer. But usually, most of the stuff I'm recording is just one mic, maybe two mics at a time, and I can get away with a pretty low buffer at that point. And Logic will tell you how much latency that represents. It'll say, with this buffer, you're looking at a 5.2 millisecond latency. And you have to say, okay, well, I'm willing to accept that. Okay, so this is something you got to keep an eye on. Every digital audio system is going to have some sort of input buffering. Sometimes you can control it, sometimes you can't. Like in a digital mixing console, you usually can't control the buffer. But you know what you can control? The sampling rate that mixing console runs at. So the buffer may not change, but the sampling rate can. And a higher sampling rate is going to get through the buffer faster. Okay? So there's one plug for why you might want to run at a higher sampling rate on your mixing console, because you could reduce the latency that way. So since you can't manipulate the buffer, that's just one idea. Unless they're being sneaky on you and changing the buffer when you change the sampling rate, which would be really annoying. Some of them do that. Okay, so once it's coming out of the input buffer, it lands in the CPU, and this is where all the work is done. So ultimately, you've got some software running that's telling the CPU what to do with this data that's coming off that buffer. And it could be doing several things on it all at once. It could be shooting it right back out to the output buffer, which we'll talk about in a second. It could be it's probably also writing it to your hard drive. So that, because remember, you don't want to, that input buffer is this living thing that is very volatile, and the data is constantly being fed out of it. So that's not a long-term repository there. So it's going to redirect that stream to the hard drive to save it. You might also be doing some processing on it while it's coming in, maybe a little bit of EQ or some reverb you're adding to it for the person with the mic to hear back. There's a number of things you can be doing. The CPU is going to try to do all those things. But you got to be careful that you don't ask it to do too much one time, because remember, CPUs have a finite ability to process stuff. So you got to think about how much work you're asking it to do. And if you're trying to reduce your latency, and by reducing your buffer, one way to make sure that your system stays reliable is by reducing the amount of tasks the CPU has to perform on that data. So if you want to add a bunch of plugins in on it and do a whole bunch of processing while you're recording it, that's work your CPU is going to have to do. And that means you're more likely to have a dropout with a lower buffer. So you've got to keep tabs on that. And most audio applications will have a CPU meter built into them. Logic certainly does. Pro Tools does. Sonar does. And you can pull that up while you're recording and working. You can see like how am I doing? How high am I on the CPU meter? And when you start getting past 60% or so on your CPU, that's when you might want to start thinking about turning some things off. Especially if you're recording or you are in a live situation where you're playing back a lot of stuff and dropouts would be bad. If you start seeing that CPU meter spiking, you're dancing on the edge of the cliff. Okay.
Does it matter if you just mute the channel, or do you have to actually turn it off?
Yeah, it certainly matters, and it depends on the software. So
like on Logic.
Yeah, so on Logic, it might, depending on what sort of processing you have on it, muting it will help you some, but not entirely. That some of that data might still be routed, right? If it's like a pre-fade bus you're sending out, that might still be processing. It kind of depends on what happens when you push that mute button. One of the things that most processors have is what's called a freeze button. And you can hit the freeze button, and what that does is essentially offline renders all of the effects you're applying. So if you've got something, if you're hitting that CPU spike and you want to let some work off of it, you can hit the freeze button and it'll render everything for that track, and essentially it'll stop processing all those plugins live. So if you've got something that you're not going to touch for a while, you say, I've got that track mostly sorted out, so I'm going to go ahead and freeze that for now, and then that frees up some CPU cycles because your CPU is not having to calculate all those effects live anymore. It's going to do it once, write it to a temp file, and then play from the temp file and disable those plugins.
So it's actually bouncing.
It's like bouncing in place, but temporarily, right? So it's kind of bounce in place, and the second you hit the freeze button again, it just deletes that temp file, and you go back to live processing. It's been a while since I've tried to figure that out in Logic, but I know like in Pro Tools, you can mute and you can disable a track, right? And there's a difference. Muting doesn't necessarily stop the computer from processing it. It just stops you from hearing it. And that is, the you hearing it part is a process that the CPU is doing, but it doesn't stop everything. There's still some stuff going on before then. So yeah, the real test of that would be to watch your CPU meter and start muting stuff and seeing if it makes a big difference. If it doesn't, then you're probably going to want to freeze stuff. But that's probably, it's different per program you use, and you just have to look that up. It's usually in the manual. They'll say what actually happens when you mute it. So, all right. So the CPU is talking to the input buffer. It's also talking to whatever software you're running to find out, what it's supposed to do with this data. And so the software would be like Logic or whatever, QLab, whatever you're using. So there's instructions going on there. There's also your internal hard drive of your computer. This is where your operating system is living, probably where your software is running from. This is so because the audio is really too large to live in RAM, it has to go to a hard drive, and you can use this is what we call the startup drive of your computer. This is the hard drive that runs your operating system. You could record to that. You really wanted to, but remember that hard drive is also busy delivering your operating system and delivering your application software and whatever else is going on. And, hard drives, you think CPUs are slow, hard drives are slower. So you have to be just as conscious about hard drive. And again, most audio programs will have a hard drive meter as well as a CPU meter. And the hard drive meter is all about how much data am I pulling off of my hard drive at one time. And the top of the meter would be the maximum throughput of the drive. And if you get to where you're at the top end of that meter, then you're in a dangerous place. So generally, that internal drive you want to dedicate to running the software. That's where you run the operating system. That's where you install your programs. Your plugins will run from there. That's where that stuff happens. The actual audio you really want to have live somewhere else. And that's where you would get like some sort of external hard drive. This could connect to your computer a number of ways. You can do USB, you can do FireWire, you can do Thunderbolt now. I would advise against USB if you can avoid it. because one of the interesting things about USB is that USB doesn't get to talk directly to the CPU, USB devices. They have to talk to this thing called the USB bus. Okay. Essentially what happens is anything that the CPU wants to talk to has to get what's called a hardware ID. It's a unique number that represents that device. Okay. USB devices don't get hardware IDs. Okay, so the USB bus gets a hardware ID, and then it then relays information between the computer and the device. So you can have 20 USB devices connected to a computer, but ultimately the CPU only really talks to the single USB bus. So there's overhead there, right? There's CPU overhead that is involved, so the CPU has to run that bus. And that's extra cycles the CPU has to run to do that, to handle that. However, FireWire devices, this is one of the reasons why FireWire is a bit more reliable for hard drives, is FireWire devices get a hardware ID. So they are treated in the same way as an internal drive is, in the sense that they get a unique hardware ID in the system, which means the CPU can talk directly to them. And other devices in the computer can talk directly to them. So you could copy data from one FireWire drive to another FireWire drive, and they could negotiate that together without having to tie up the CPU, for example, if the drivers are written correctly. So that's why FireWire tends to be preferred in the audio world, is because do you want? And it's ultimately a choice. The USB will work, but you're going to take a CPU hit by doing that, and that CPU hit might be the equivalent of one less track that you get to run in your audio program. And maybe if you don't have a lot of tracks, it's not a big deal. But if you have a lot of tracks, maybe you do want that extra track. So that's why FireWire is really great for that. Although FireWire has a limited throughput, so the FireWire 800 is basically 800 megabits per second, whereas the internal drives these days are really working on what's called serial ATA as their bus, and they can do like 6 gigabits per second, which is quite a bit. So there's a bottleneck there, and that's why there's a push now for a faster interface, and Thunderbolt appears to be where that's headed at the moment for the audio world. We'll see how it goes. Generally speaking, FireWire, as much as I say there's a bottleneck there, it's usually mostly plenty sufficient for what you would need to do audio-wise. But you can get better performance out of a Thunderbolt or a second internal drive. So if you don't have a laptop, for example, and you've got a big tower computer, you've got space for a second drive, and you could dedicate that to audio, put it inside and hook it up to that serial ATA bus, because then you get a 6 gigabit pipe to hook it up to, as opposed to the 800 megabit FireWire pipe, which is quite a bit slower. But the important part of this is that you really want to have a dedicated hard drive that just does sound. All right, so there's nothing else on it but your audio. And that way, the computer isn't using it for anything else, and you can rely on it to deliver and capture the audio consistently. So let's see. The display. So this is your video monitor. This is where the computer will sort of show you what's going on. It has your interface, where you see the pictures of the waveforms and everything. An interesting thing to know about this, though, and this is kind of something you have to keep in mind, is that I say that on the interfaces you have these little meters that will show up on your screen for CPU and hard drive. Well, when you really start taxing your CPU, it's going to start prioritizing tasks. Okay, it's going to start to say, okay, I'm having a hard time keeping up with all this work, so what is the most important stuff? And I got to make sure I'm doing that for sure. And guess what? Audio is prioritized over screen refreshing. Okay, so if the CPU starts trying to prioritize stuff, it's going to say, well, I really don't want to drop out the audio, because that will be not good. So if I've got to offload something, I'm going to offload how often I refresh the screen. Maybe I'm refreshing it 100 times a second. Maybe I only have to refresh it 5 times a second, and then that frees up some time to keep the audio flowing. Well, so what's that going to do to you if you're looking at your CPU meter and waiting for it to see if it clips?
So you're 5 seconds behind.
Yeah, basically, yeah. So your CPU meter, you could clip your CPU and never actually see it, because the computer was not redrawing the screen. Okay, so that's why I say if you ever cross like 60% or so of your CPU meter, that's when you want to start paying attention. Because once you get past the 60 to 75%, now you're in the range where the computer might start dumping screen refreshes, and your meter's not going to be very reliable. That's just a little thing I learned the hard way. Your CPU could be clipping like crazy, and you'd never see it. Because by the time you get to the point where you're clipping the CPU, the screen is not refreshing very often. and then your audio just starts dropping out, and you say, hey, what was going on? My meter was fine. All right, so the audio comes back out, so now you're going to play it back, and the CPU is going to take that audio stream, it's going to pull it off the hard drive, it's going to run it through the CPU, it's going to apply whatever processing you want to it, and then it's going to shoot it into RAM again. And it's going to make an output buffer now, for the same reason it made an input buffer, because that way it can consistently deliver that stream, because audio is a real-time thing, and you don't want to wait for it. Okay? It's not acceptable for it to give you a little bit of it, then wait a second, and then give you the rest. Okay, it needs to be a consistent stream, so it's going to make an output buffer to help even that out. Okay, and again, you can usually control that, how big that buffer is. The bigger the buffer, the bigger the latency, although generally with playback, latency is not as big of a problem as it is with recording. So coming out of that output buffer, it's going to go down whatever cable or whatever interface you have to the computer, and it's going to go into your DSP controller chip on your audio interface. And that's where, again, you could be doing some stuff to it. Maybe you're going to add some reverb for monitoring purposes or whatever on there, so your CPU is not having to do it. Sometimes singers like to hear reverb in their headphones. And you could put a plug-in in Logic to do that, but then your CPU and your computer's having to process that. Reverb's, that's a big job for a CPU to do. So that's why some interfaces have built-in reverb, like those Motus have built-in reverb. And the whole idea there is you can just dial in a crappy reverb, and the interface will do it. So your CPU doesn't have to, and then the singer can hear a little bit of reverb in their headphones, and you're not having to tax your CPU doing that. So that could be happening inside this chip. But ultimately, the most important thing it does is it takes the data that came in out of that RAM buffer, and it runs it through a digital to analog converter, and this is the opposite of the first one. So now it's going to take those digital values, and it's going to now convert them back to voltages. Okay. So coming out of that DAC is going to now be a voltage wave. And then that's going to interface some way. There's going to be a physical, quarter-inch or XLR or whatever output on your audio interface, and that's going to have the voltage on it. And you would plug in, either your headphones in this case, or your monitor loudspeakers, or your mixing console, or whatever it is. At that point, it's analog again. That's how the computer does sound. Yay! It's very simple. Okay. It is really. It's not nowhere near as complicated as it might seem. Okay. But if you understand, the whole point here is I want you to understand all these different steps, because when you have problems, you need to know where to attack it. If you've got dropouts, for example, where's that coming from? Is it because your buffer is too small? And if it's your buffer is too small, that is a symptom, but that is not necessarily the problem, right? If the buffer is too small, it's too small because some other component of the system is not keeping up. Okay? And what is it that's not keeping up? Is it your hard drive? Is it your startup drive, or is it your external drive? Is it the CPU that's not keeping up? Is the software that you're running too slow to do? Maybe it's not capable of doing what you're trying to do. Where's the bottleneck? The short-term fix is increase the buffer, but ultimately you want to try to zero in on why the buffer wasn't keeping up to begin with. And it could be that you realize that, oh, I actually saved this to my startup drive instead of my audio drive, and so it's been running off of my startup drive all the time. My startup drive is busy doing all these other things. So maybe that's my problem. I'm going to try putting it on this external drive and then running it. I'll give you an example of this problem. I don't know if, I think it was Alicia on Random. They were having some dropouts on QLab. They were playing back sound, and it turned out that I came in and looked at it, and it turned out that what Maria was doing is she had her external FireWire drive, and she was taking it down a tech table. She was creating all of the audio files and cues, and shaking up and just plugging her FireWire drive into the Mac up there, playback, and then streaming those files off of that FireWire, which is normally would be probably okay, but in her case, she was playing a lot of stuff, like it was big, massive, multi-channel audio files, and the FireWire bottleneck was becoming a factor. So the FireWire, that 800 megabits per second, was not keeping up, and so yeah, and then because then we moved it to the built-in, because inside that iMac is a solid-state disk, startup disk, and it's almost as fast as RAM, and it's got sitting on that 6 megabit per second bus, and the only program you're running is QLab. So the CPU is not all that busy doing a whole lot of other things. I mean, I try to make sure that you guys don't connect those to the internet. That I've uninstalled all of the other programs on it. There's nothing else on it that you can really do, so that all you're doing is QLab. And so we said, well, hey, let's move this off of this FireWire drive, put it on the startup drive, since that startup disk, normally the startup disk is slower, but in this case, the startup disk might actually be able to perform faster than this FireWire drive. So we put it on that solid-state internal FireWire drive, and it was fine. Internal startup drive, and it was fine. Worked great at that point. Yeah. Now, if that hadn't worked, then the other solution could have been, well, maybe we need a couple of drives. Maybe we need to take some of this audio and spread it across more than one drive, so there's not one hard drive doing all of it. Or maybe we need to, take a drive and interface it with a faster bus. So maybe FireWire is too slow. Maybe we need to put this through a Thunderbolt connection and get more data to push through. I mean, there's any number of ways you can do it, but ultimately, that's where the problem was. And we could potentially go in and manipulate the output buffer, and you can do that in QLab. You can manipulate the size of the output buffer, but really the problem was that you were trying to push too much data through that FireWire drive.
It took us a couple days to figure out, because the couple of times that you came to help, Maria wasn't in there with her hard drive.
Right. So we weren't having the problem, and then finally we realized that the problem only happens when Maria plugged in her FireWire drive, and we said, we must be trying to push too much data through that FireWire drive. Okay, so there's really not that many variables in here, though, and that's the point I'm getting at, is if you're trying to troubleshoot this stuff, think about all these different steps and think, well, based on what I'm seeing and hearing, where are the places that in this chain that can make that happen? Yeah.
I don't have a question about this, but what is an Oxford chipset?
Oxford chipset?
Yeah.
So if you've got this external hard drive, let's say that this is a FireWire drive. What happens is there actually isn't such a thing as a FireWire hard drive. The hard drive itself is going to be probably a serial ATA hard drive. And you're going to stick that inside of a box that has a FireWire chip on it. And there has to be a little bit of software on that chip that translates the serial ATA stuff into FireWire and vice versa. And so the chipset, we call that the chipset. So there's the chipset on the little interface that does that FireWire to serial ATA conversion. Okay, and this used to be more problematic than it is today, but for a while there were a few different chipsets floating around for FireWire hard drives. There was the Oxford chipsets, and there was another one called the Prolific chipset. And the Prolific chipset proved to be really horrible for sound because it was not particularly good at continuous, long-term streams of data. Like it was really good at delivering big amounts of data really fast, but it wasn't so good at keeping up with a steady stream for some reason. And the Oxford was, and is. And so for audio, when we were buying these FireWire hard drives, we found out pretty quickly that the Oxford chipset performed better and didn't drop out as much. And so, and it was really DigiDesign who zeroed in on this with Pro Tools. They started supporting FireWire drives, and they started seeing varying levels of performance, and they were the ones who noticed with Pro Tools that, we don't have these problems with the Oxford chipset, but we do with others. And so in their specifications, they said, look, if you're going to use an external FireWire drive, it has to be an Oxford chipset, or we won't support it. And so that I've now relayed that same information to you guys when I make you buy your FireWire drives. I say, if you're going to get a FireWire drive, make sure it's got the Oxford chipset, So that's the one that is proven to be most reliable for sound.
Yeah, I knew that. I just didn't know why.
That's why.
How do you even look that up on a device?
Usually it'll say it in the specs for the drive. If it doesn't, you can call the manufacturer and they'll tell you. Let's see. Let's look one up here.
I went to Apple. I know it's about hard drive. I was talking about it, and they had no idea.
Yeah, I mean your average sales rep is going to have no idea.
Well, I would
You've
guess
got-
the geniuses apparently didn't know.
Yeah, but they're not the ones who make that drive. You got to talk to the person who made it. So careful, you've got one right here.
I love them.
She
They're great.
actually is.
I love them.
Let's see.
It's okay. Go
Here we go. So Oxford 944 chipset for the FireWire. So you got to go to the place that makes. So Apple's going to sell you the drive, but they didn't make that drive. LaCie made that drive, and Apple's reselling it. So who made it? Go talk to that person. They'll tell you.
Seagate, Western Digital.
Yeah. So there you go, right there in the spec sheet. If they don't know, and you call the guy in the basement with the white lab coat, if you can get past the tiers of support and everything, actually get the person who actually used the soldering iron and put the thing together, and he doesn't know, then don't buy it because you never know what it's going to be.
So what would be the best configuration? A solid state through FireWire?
Yeah, well, I mean, I don't know. Solid state isn't necessarily going to be any faster through FireWire because ultimately you're limited by that 800 megabits per second. Okay, and so you can put that 6 gigabit per second solid state drive in there, but it doesn't mean you're going to get to push 6 gigabits per second out of it. So the FireWire bus is going to be the bottleneck. So what the solid state gets you is durability. So that's why I have two in my bag. So I have two external drives, two of these actually. So one of them is a solid state, and the other is a traditional hard drive. So why both? Well, the traditional hard drive has a larger capacity, so it can store more data on it for less money. I mean, solid state is still expensive, right, per gigabyte. But the solid state one is more reliable. Right? It's less likely to crap out. It's not going to stop spinning or something, for example. So I tend to, it's not that one is faster than the other, it's just that the solid state one, I tend to put on here the things that I'm working on right now. So whatever the current projects are, live on there because
And they're all through USB.
FireWire. So these are both
FireWire.
FireWire. This, I mean, they're hybrids. They do USB as well. And then I put the long-term stuff on there. However, this has a USB 3 interface, which USB 3 is pretty fast, actually. It's like, what is it, 3 gigabits per second or something?
USB.
USB 3?
Yeah.
Yeah. So it could push quite a bit of data, but it has that CPU overhead to do it. So a lot of times what I'll do, if I'm like just pulling stuff off of this drive, if I'm like trying to get something out of an archive, or I have like a sound effects database on here that I pull stuff off of, I'll go ahead and hook it up USB because I'm not looking for continuous throughput here. I'm just looking to get a big chunk of data off of there really quickly and put it onto this thing. In that case, the USB 3 would work really good for that. I wouldn't necessarily want to use that for recording unless it was a small recording. I have done it before with a recording just as a test, and it was like one mic and it was fine. But if it was a lot of channels, I may be less likely to want to use that USB. But some people have had really good success with USB 3 these days. The CPUs are getting such, we kind of crossed this line. This really, the video world really helped us in sound because when people were trying to do video on computers, the computers had to get beefed up quite a bit to do video. And consequently, the CPUs now are almost over-spec for us. We crossed a line about 5-6 years ago where the CPU became more capable than our ideas. And for years prior to that, we always had way bigger ideas than our tools could pull off. And we crossed a line somewhere, like say 5-6 years ago when it's now even running something logic with lots of tracks and everything, the CPU is still quite happy. And so we're in pretty good shape these days. We don't have to be quite as concerned about CPU anymore. And so that's all I was saying. That's why you're starting to see manufacturers put out more USB audio interfaces, because it's like, well, we can take that CPU hit now because we've got some headroom on the CPU that we didn't used to have. But your mileage may vary. That being said, you can get drives that do Thunderbolt, and those theoretically should be just as fast as the internals. Here's they make a Thunderbolt equivalent to this drive, and let's see what it says. It should be able to do 10 gigabits per second, which is pretty good. That's pretty good.
How expensive is getting the Thunderbolt onto a system?
Well, if you don't already have it, you got to buy a new computer.
Oh, really?
Yeah, I mean it's what Thunderbolt is it's basically a direct connection into the motherboard, basically, right? So it's the equivalent of putting a card slot, in a PCI slot. It's that fast. So if you don't already have it, there's not a way to upgrade the system to have it. It's part of the chipset of the computer. But most of the Macs that have been shipped out in the last 4 years have Thunderbolt on them. So if it's more than 3 years old, you might there was a period of time there about 4 years ago where they were selling both. They were selling some systems that had it and some that didn't. But most of them these days have it. So if you don't, yeah, you've got to unfortunately buy a new computer, or just don't use Thunderbolt. It's fine. But yeah, I mean, we're all very excited about Thunderbolt here in the audio world because the throughput there is pretty amazing, and that's been the last bottleneck really for us that we've been dealing with. The CPU left us in the dust a few years ago. The software is pretty solid now. The interfaces are getting pretty good, especially now with the AVB stuff. And so the last bottleneck has been the external drives, and the Thunderbolt looks like it could be the answer to that problem. Although it has its limitations. You can't daisy chaining them is less straightforward than Thunderbolt, or than FireWire was. FireWire, you can daisy chain 72 FireWire devices off a single bus and no problem. Thunderbolt is trickier on that. Not all Thunderbolt devices have 2 ports on them. And you can't make a hub. There's no such thing as a Thunderbolt hub. It has to have a direct connection to the computer. So that's the sketchy part. So you can, if you want, you can usually get a device that would have what they would call a repeater on it. So you could plug the Thunderbolt into your computer, and then there would be another port you could potentially hook another device to. But I don't know what the limit is for the number of devices you can put in. But most of these external portable Thunderbolt drives only have the 1 port on them. So here's this one, just has the 1. So you're not going to be able to daisy chain anything off of this. So you eat up one of your precious Thunderbolt ports by doing this. And then you can't use it for anything else.
It's really annoying.
Yeah, and so my laptop has 2 of them, but it has no FireWire, so I have to have a Thunderbolt to FireWire adapter, and that chews up one of my Thunderbolt ports. And then I don't have Ethernet either, so I have to have a Thunderbolt to Ethernet adapter, and there's my 2 ports right there. So to get a hardwire Ethernet and talk to my FireWire drives, I'm now out of Thunderbolt ports. So that's kind of a bummer. But that's what's so cool about the new Mac Pro, is it has 6 Thunderbolt ports on it. Yeah.
It's so nice.
And it's like, whoa.
And they actually have a rack mount for the Mac that you just put
Yeah,
in.
so
Place
Sonnet
it, and where the air passes, it doesn't get covered by it because there's holes for it.
Yeah.
And it just sits in the rack. It's
Yeah,
awesome.
Sonnet made a rack unit for it.
Yeah.
So that's cool. All right.
Slightly better.
Let's see. I think. What? Any other questions?
You carry the display with you.
Let's see here.
It's casual.
Was there anything else I was going to show you? Oh, let me show you this real quick, guys. We were talking about buffers. So here is an example of using digital devices but connecting them analog, and which means you're doing a conversion at each input and output. And remember how much latency you get with each conversion?
So you're introducing 3 milliseconds.
Yeah, well, theoretically, you get a millisecond here, so that's 1. You get another one there, 2, 3, 4, 5, 6. You get potentially 6 milliseconds of latency in this system from the mic to when the sound comes out of the loudspeaker. There might be more internally that you are introduced to with some buffers and things. So one way to reduce that is to, oops. Here we go. So you could potentially collapse all those processes into one digital device, which, you know, that's the great thing about digital is instead of having all these dedicated devices like you used to have with analog, you can actually have one device do a lot of things. Or if you do need separate devices, you can interconnect them digitally. So if these interconnections are not doing analog conversions, then that you've now taken out 1, 2, 3, 4 conversions out of it. That's potentially some latency you can avoid. The other thing you can do, this is just an example of how the buffer works. So this is a buffer, and here's the audio. It's coming in, and your first sample hits the buffer, and then it travels through. And in this case, it's 44.1 kilohertz, so you get the sample step forward every 1/44th of a second. So that sounds really fast, but you can hear that. So you don't actually get to hear that first sample until it gets all the way out of the buffer. So there's some latency that goes on there. And you can actually, this is how they know. You can predict it. So the math is you just take the sample size of the buffer and you divide that by the sampling rate. So if your buffer is, in this case, 32 samples, and your sampling rate is 44.1 K, that's going to give you 0.000725 seconds or 0.725 milliseconds. That's not much of a latency at all. That's no problem. But if your buffer was 1024, which is usually the highest one you can make, let's do that math. 1024 sample buffer divided by 44100. Now we're talking 0.023 seconds, so times 1,000. It's going to be 23 milliseconds. Well, that's enough to cause you a problem. You can hear that, okay?
That's an hour.
Yeah, if you're talking about fold back into a set of headphones, you could hear that, okay? So it's very simple. So predicting this is very simple. That's what I'm getting at. But the interesting thing is, assuming you have the same size buffer, this is where I was getting at with the mixing console, you can reduce the latency by simply increasing the sampling rate, right? Then the math bears that out, right? If the buffer is static, sampling rate goes up, the result is going to go down, okay? So we've just animated this, the same size buffer, but one running at 44.1 kilohertz, the other running at 88.2. Okay, the sound gets out of the buffer in half the time. So you've cut your latency in half there, just by increasing your sampling rate. Now you haven't necessarily made it sound any better, right? Because we know just increasing the sampling rate doesn't necessarily get you better sound unless you add all the other components required to capture those frequencies. But simply increasing the sampling rate could reduce your latency in some situations, purely because it's running through there faster. Okay, so that's what I was talking about when I said that.
I don't know if this will help anyone, but I found another way of getting around that latency is listening to the sound that you're recording live,
Right.
rather than
Yes.
You won't have any latency, and then when you go back to listen back, it'll be okay, because it'll still be there.
I have another. Yeah, I've got a thing of that. That's the next one in here, actually. It's called direct monitoring. So, so here's our diagram of the system again, right? And we know the microphone, it goes into the preamp, and that goes into the converter, and we know that there's latency going on ultimately inside that input buffer. Okay, and we know that the CPU is going to have a hard time keeping up, but it ultimately puts it through an output buffer that then goes out. So if you're going to listen to this back, it's got to go through that output buffer and then through the converter, and you're picking up latency all along the way before you ever get to hear it in your headphones. So it goes through the buffer twice, right? It goes through the input buffer, and then it goes through the output buffer, and that's why. So the latency ends up getting doubled. So that 23 milliseconds turns into 46 because it goes through two buffers before you get to hear it again. And 46 is an audible echo. Anybody could hear that. So direct monitoring, how does that work? Well, what if you could introduce a little switch that could tap into that analog signal before it gets converted and shoot it straight back out to the headphones? You would essentially have no latency now, right? Because you're completely bypassing all the RAM buffers, completely bypassing the converters. No latency now. So a lot of audio interfaces have this now. There's a switch on it that you can say direct monitoring. And what it does is it basically folds the input straight off to the output before it goes through the converter. And then, yeah, you get no latency. And then you can get away with the higher buffers on your computer, and it's no problem. You get the reliability. So yeah, it's called hardware direct monitoring. And it's quite handy. There's also a thing called software direct monitoring, and what that's doing is usually that's happening still in the audio interface, but it's bypassing the RAM buffer because it's doing the tap after the digital conversion. So at that point, you're only getting the 2 milliseconds, whatever you get with each one per conversion. So some software drivers. So here's like the this is just a screenshot from like the ASIO driver for some interface. And what you're doing there is you're sending a command to the interface itself, and you're saying, hey, take the digital signal coming in on the input and route it to the output. And that's called software direct monitoring. And in some cases, some of your like workstation software, like Logic or Pro Tools, has an option for this, but it's really communicating to the sound card, telling it to do that. So that's, if you don't have the actual hardware direct monitoring, you can do it this way, and it's not quite as good, but it's better than letting it go through the RAM buffers first. So that's called software direct monitoring. So, you can do either or. So as it's saying, I don't know if you can see that really well, but there's no latency with the hardware monitoring, but we're getting about 2 milliseconds with the software monitoring. But 2 milliseconds is better than 46 milliseconds. Yeah. But so that's what you're talking about, Jim, is this, right? So very helpful. And as yeah. So we were saying here that this going through these RAM buffers, that could be anywhere. It could be as high as 100 milliseconds, depending on how big your buffers are. And that's a lot. That's really hard. That's hard to listen to. Okay, let's talk about any other questions or comments. Okay, let's talk about this assignment I emailed out to you guys last night. Everybody got it? Okay. So what you're going to do is you're going to pretend that I have absolutely no information, but I have a dream. I have a dream that of recording my own album. I've been practicing my guitar, and I've been taking singing lessons, and I really think I've got it. I've got it, and I'm ready. I just gotta lay some tracks down. okay, and get it out there, and then the world is going to love me, okay? And I've been working at the snow cone shack in the summers to save up my money, and I got
so glad this is being recorded right now.
and I got $3,000. I've managed to save $3,000, and I think that that's going to be enough to record my demo. So I need you now to get me what I need to do this. I want to record my own demo. Okay?
Is
So
that including the price of the computer?
yes. So
How can you do it on a
Yeah,
Mac?
question. Is it, because I was reading.
it is
the
possible.
Is it $3,000 for the Windows and then $3,000 for Mac, or is it
Yeah.
just $3,000?
So $3,000 for each system.
Okay.
So I'm saying
So it's
ultimately I have $3,000 to spend, and I have no particular ideology when it comes to computers. Never used one before, but I'm getting really good with this guitar. So I don't really care which one. So go tell me both. Show me what it would look like for either one. But it can't be more than $3,000. And I'm a student, so I can get a deal on some stuff, educational discounts. Okay, so that's the other part of this story is I'm a student. So so if you can find an educational discount on software or the computer or something, that could help. But $3,000. So yeah, I want you to spec a $3,000 Windows system and a $3,000 Mac system.
So it's $6,000.
Ultimately, you got $6,000, but
But it's all $3,000.
it's only $3,000. Okay, so Corey and Jay Shell and Alicia, that's what you're doing, and I've got the specs there. I've got I say I need a mic. I want to be able to do a little bit of keyboard stuff, because I'm working on that a little bit. Maybe I can,
Cables too.
yeah. So I want the keyboard. I need the headphones so I can hear myself. I need the computer. I've heard that Logic is pretty good, so let's use that. And I've heard I need to have the Waves plugins because they've got a really killer reverb on there. So I want the native Power Pack Waves. Somebody told me that was really good. So give me that. So anyway, I've got the list of all the stuff. And so what you got to do is put together a quote, right? Go out and find sources for all this stuff. What can I pull off for $3,000 that will meet those minimum requirements?
So you don't have to have the speakers. You can just buy the monitor. Use headphones.
Yeah, I don't think I put loudspeakers on it. So I'm quite happy with headphones. Okay, so some of the requirements are not explicitly stated there. Right, there's some implicit requirements there that you have to ultimately deliver on. Like the cable, or power. I mean, whatever. Right. So for the grad students, you also have to do a playback system. So now I'm going to be another. Now I'm the technical director of the little community theater down the street, and we've heard that this QLab thing is really cool, so I want to get into that. I want to get in on this QLab thing, or the SFX thing, which I know is a thing as well. So
Spec the Mac side with QLab, spec the Windows side with SFX.
Yep. So ultimately, the grad students are going to spec 4 systems for me, which is how you earn your graduate level credit. And the undergrads are going to spec me just the.
Would it really be 4 systems, or would it just be 2 systems that do double?
Yeah, you treat us 4 separate things,
okay.
Right? So $3,000 to get me a playback system, or $3,000 to get me a recording system, but they don't have to do both. Okay. So what I want you to do is go out, find the stuff, figure out where you can get it, get a good deal on it, and then what I want you to turn into me is an itemized quote, okay, that tells me, all right, you can get a computer from this place for this amount of money, and here's the link and all of that you would need, because ultimately I'm going to check you. Once you turn it in, I'm going to pretend to not going to be me now, and I actually know this stuff, and I'm going to check your work and make sure that this would do it if I spent the $3,000 and I got all the stuff and I plugged it up, would it actually work? Okay, so I need to be able to, you can't just say, oh, I found you, a MacBook Pro for $500. I'm going to want to see that link. Okay.
What if I didn't know a guy selling a MacBook Pro?
I need to be able to call him. Okay. Say, hey, I hear you're selling a MacBook Pro.
Okay, that's all I care about. Goodbye.
Right?
That's fine. That's easy.
You almost have to use a MacBook Pro. You can't use anything else. Everything else, I mean, a Mac Pro would be $3,000.
Yeah, a Mac Pro, you
You're not doing a Mac
can't do
Pro.
that, right? So what you got to look at is what are the minimum specifications for what I've got to do. For saying I want to do Logic. What's the bare minimum that could pull off what I'm talking about, and you got to have the computer that can at least do that. Yeah, certainly, I'd love a MacBook, a whole Mac Pro tower, but that's not going to happen with $3,000.
And a Mac Mini's not going to happen either. You have to buy everything.
Yeah, I mean the Mac Mini could do it, but then you got to buy a screen and keyboard. I mean, that might be less expensive ultimately than even the laptop. So that's kind of part of what I want you to figure out. By the way, I get asked to do this all the time. I don't know. So this is like a real thing. I mean, people come in, oh, I want to do my album. So
we're doing 4 systems. So that's 4 different computers? Yeah. Okay.
potentially, yeah, because with the playback system, you're gonna be spending less on you're not gonna buy some stuff, right? There's some you don't need a microphone for the playback system, so that's more money you could spend on the computer or something else, right?
Okay. Cool.
Okay. So this is just an exercise in can you interpret a spec sheet, right? Can you read a spec sheet and that has requirements, and then find hardware that delivers on that? And can you wrangle a budget, right? Those are the 2 goals. Because remember, my rule is never, ever, ever ask anybody to spend money on something for you unless you know absolutely sure that it's going to work and they will be able to hear every penny of that money they spent, okay? So that's what I want to make sure is that if you're going to tell me to spend my hard-earned $3,000 from the snow cone shack, that I'm going to actually be able to record my demo. But I'm not going to spend that $3,000 and have a pile of stuff that I can't even, I can't even turn it on because you don't even have the right cable to plug the 2 things together, right? Or you forgot the dongle that makes the plugins launch, so I can't run my great reverb that I wanted because you never bothered to buy the dongle. Okay, so that's the kind of stuff you want to look out for. What are all the different requirements? Make sure you meet them all. I think you'll find that the $3,000 is more than sufficient. Yeah. It sounds like not a lot, but
you can get a lot.
You can do it. It's totally, totally doable.
And do you want cases and stuff in case you want to?
So yeah, for you guys, for the playback system, I did say it needs to be in a rack because we're gonna be shuttling this all around. Because if I'm Joe, Community Theater Technical Director, I'm gonna loan this out to 3 other theaters in the area when they call me because they're poor too. I'm going to say, yeah, sure, you can borrow my QLab system. I'm not using it this month. And so it's going to get thrown in someone's truck and driven across town. So yeah, it's got to be in a rack. Okay.
This is so exciting.
Now, let's say hypothetically.
Yeah.
Well, when is this due, first of all?
I don't know. When did I say?
I don't know. You didn't say.
I did say.
Are you sure it's
Monday.
I think it's Monday, right?
Monday.
Yeah. So Monday, I want this. And email it to me. Don't give it to me on paper, please. I will lose the piece of paper if you give it to me.
If we find links to specific places where you can buy specific things, do you just want us to plop it in an email, or do you want it in
Put the link in the spreadsheet. I mean, just if you found the deal of a century, and and I'm not going to be able to find that on my own. Yeah, I want the link, so that I can verify it.
Now, let's say hypothetically, I have a link.
Yeah.
But I know somebody high up at this store who I'm not kidding, who can get me half off.
I need to be able to call that guy.
Okay. So make sure you call them.
I'm gonna find that another $500 MacBook. You're getting a Logitech microphone, and
Yeah, I mean, I don't care where you get this stuff from. You can be resourceful,
Okay.
but ultimately, I need to be able to verify it.
Okay.
This deal.
So you can buy my laptop.
Right?
$300. Take it. Please give me an A.
I mean, that being said,
Gonna sell his computer.
I wouldn't go, in the spirit of what we're trying to do, I wouldn't go hog wild with calling in favors. I'm willing to entertain that, but I would start by just could I just whip out my credit card and go buy something right now? Let's start there.
Yeah.
And then if you need to start wheeling a deal in,
Let's get it really.
Yeah,
All right, so it's due Monday.
You got PayPal.
What's up?
Wanted to check.
Like Santa.
I couldn't open up your directions. QuickTime refused to allow it because I was doing it on a PC. But I always use this Mac
Okay.
for.
Oh, hang on. Let me turn my video off here.
One of the